Let's have a look at this idea of vectors via what we've been looking at, the translation of graphs. So imagine we've got our basic parabola and we're going to translate it 2 units to the right and 1 unit up. And we want to find the equation of the new parabola. Well, we know that x squared, well, we've shifted it, so it will become x minus 2 squared. And then when we shift it up 1, it becomes x minus 2 squared plus 1. So it involved 2 shifts there, one horizontally and one vertically. But of course, we could do it with just 1 shift diagonally. That's what we call a displacement vector. So how that curve has been shifted, how it's been displaced from its original position. And in fact, you could pick any point on that parabola and every single point would be moved by the same displacement vector. They'd all be the same. We could then create our equation. I've written it in what's called column vector notation, and we'll talk about that in a sec. But the new one, so I've used capital X to represent the new one so we don't get confused. But that new xy is the old xy, so the little xy, but I've added, and you'll see in the one vector there, I put both shifts in. 2 in the x direction, 1 in the y direction. And then we simply use parametrics to come up with the equation. Because, all right, I said little x and little y, but I could say it's t and t squared because we knew the equation of the original one. We knew y was equal to x squared. So if I change that to t and t squared, then I create these parametrics, add them together. I've got t plus 2 on the x and t squared plus 1 on the y. So rearrange that, make t the subject, substitute it into the other one, and you see we get the equation we were expecting. So that's translation of graphs, but basically it captures the idea of vectors. So some definitions. So what I just talked about, that vector where we moved every single point, how the original curve was displaced to the new position, we call it the displacement vector. Now how I write that's very important. You see the arrow over the top there and the order of P and Q. P is what we call the tail of the vector, so where the vector started from. Q is the head of the vector, where we then displaced it to. So it's going from P to Q, hence why we write it the way we do, because reading from left to right, we're saying we're going from P to Q, the arrow is giving us the direction. We're going that way. Some other notations that we use. Now, the first one, not real useful when you're handwriting. Sometimes you write the letter in bold. Well, how do you do that when you're handwriting other than writing over it a whole heap of times? So we don't tend to use that much when we're handwriting our solutions. More common is the second one there, where we just put a tilde underneath the pronumeral. Now, it becomes really important whether that tilde is there or not, because it becomes the difference between a vector and a pronumeral, and they are different things. So every vector can be uniquely identified. So whilst I move them round, they maintain 2 things. They maintained the length of the vector, that didn't change. Every one of those displacement vectors were exactly the same length, or magnitude. But the other thing is the direction it's going in. That's the other thing. And just like we saw with trig, we tend to measure the angle to the horizontal. Notation for magnitude is the absolute value symbol, because that's really what absolute value is saying, the magnitude of the number. So it could be magnitude of P with a tilde underneath, or magnitude of PQ. It just means the size or the length of the vector. Now, opposite vectors or negative vectors are simply vectors in opposite directions. So if PQ was the vector P, then QP is going in the opposite direction. Well, that would simply be negative P. Same vector, but just going the opposite way. Parallel vectors, well, as the name suggests, if they're parallel, they'll have the same slope. So PQ would actually be parallel to QP, because they are going parallel to each other, they were just in opposite directions. Then there's this very special vector, the zero vector. I've written it a really strange way. PP. Starts at P, finishes at P, goes nowhere. Hence the name zero vector. The other probably more common way you see it is with just the number 0, but with a tilde underneath, so you know you're talking about the zero vector, not the number 0. They are essentially the same thing. But here's the interesting thing. It doesn't have magnitude. Well, that makes sense. It's not going anywhere. But it also doesn't have direction. Because if it's not going anywhere, well, how do you know in which direction was it heading? But therefore, it makes it parallel to every vector, even though it's not going anywhere. I know that sounds strange, but the zero vector is parallel to every vector. A scalar is just the size, and if we don't give it direction. So it's just a number. We could write it like this. Very common in vectors that we use the Greek letters for the scalar and our normal letters for the vector. It doesn't have to be that way, but it's quite common. So lambda p, so lambda is a scalar because it doesn't have the tilde underneath. P is the vector, and that's what I was saying. It's important, the difference. You see the tilde underneath, you know you're talking about the vector, whereas it's not under there, it's just a pronumeral, so it's some scalar, it's representing some number. But it would have a direction of p, it's just longer. We've just multiplied its length. Now, a position vector as opposed to a displacement vector. A position vector, the tail's at the origin. So if the tail's at the origin, we call it a position vector rather than a displacement vector. How do we play with them then? Adding and subtracting vectors. And we always add vectors head to tail. So we join up the head of one with the tail of another. So here's vector A. If I want to add vector B, I would just slide the vectors so the head of one meets the tail of the other. So I could do it this way. There's A, add on B. The new green vector would be whatever A plus B is. That's the new vector. But it is commutative because addition is something we can do in either direction. So B, I could have done that one first and then added A. So B, A, but you'll see we get exactly the same vector. Doesn't matter which way you do it. Another way of expressing that, PQ, so the vector PQ, there it is, plus the vector QR, on the vector QR, would end up being the vector PR. The way you can think about it is if you're adding two vectors, it's like you're smashing them together and the Q disappears. So you've got PQ plus QR, smash them together, I've got PR. If you want to subtract the vectors, then you place them head to head rather than head to tail. That can get a bit confusing. Possibly an easier way of thinking about it is you add the negative vector, because the negative vector is when it changes direction and the head and the tail swap around. So there's A. If I wanted to subtract the vector B, the way of thinking about it is saying, well, I'm going to get A, but I'm actually going to add the negative vector B. So the head and the tail swap around, and now I can just simply join the head to the tail like I do normally. So there's my vector A minus B. Here's the interesting thing. If you were to create a parallelogram by using both of the ways you could do the A plus B, then the diagonals of that parallelogram become these two vectors. One is A plus B, one is A minus B. Let's have a look at that. There's A plus B if I'd done it that way. If I'd done it B plus A, we end up in the same spot. Has to be a parallelogram because we know they're equal vectors, so they've got to be parallel. One diagonal ends up being A plus B. One diagonal ends up being A minus B. You'll notice with A minus B, I called it A minus B, not B minus A. Head minus tail. Always head minus tail. See where my arrow is? The arrow's at A. So the head is A minus B. If I had the arrow at the other end, this vector would become B minus A, or the negative vector. Well, multiplication of vectors by a scalar. So just by a number. What happens? Well, what we said before was it simply increases the length or the magnitude of the vector. So there's A, there's 2A. Simply doubled the length of the vector. The direction does not change. That one would be minus a half A. So I've halved the length of the vector, but now it's going in the opposite direction. So the head and the tail have swapped around. But they're all parallel, because as I say, the basic direction has not changed. Well, one's negative, but it's still parallel. Okay, so let's have a look at this little problem. And I just noticed in my PowerPoint there that I must have overlaid it and I'm missing the tilde on the A and the C. They are actually there, it's just covered up by the line below. I put it too close. What's it look like on your sheet? Have you got the tilde there under the A and C? So you might want to add those in. So AB, I'm just going to call the vector A. AC, I'm going to call the vector C. P and Q are midpoints of those vectors. And R is placed so that the vector RC is twice the length of BR. Okay. Well, let's find expressions for the vector BC and PQ in terms of A and C. They're the only two that we've defined so far, A and C. So the question is then, BC, how can I get from B to C? I could do it this way. Remember, the only ones I know about is AB and AC at this stage. I could say it's AC minus AB. Right? AC minus AB. If you have a look at our picture, AC, if I went all the way from AC, but then took away, so now this is going in a different direction, AB, I would get that. Or another way of saying it is head minus tail. BC, so I've got AB and I've subtracted AC, that would give me the head minus tail of BC. So that would be C minus A. Okay, PQ then. How do I get from P to Q? Well, it's a half of AC minus a half of AB. Remember we said these were the midpoints. So they're the same vector, but half the length. So that's a half of C minus A. Compare the vectors BC and PQ. You got to hate questions like that. Well, what do you mean compare them? Oh, one's in red, one's in blue. What are you talking about? Basically, it's saying that. How do they relate to each other? So PQ, that we just found over there, and BC, the obvious comparison is, oh look, one's half the other one. So what does that tell you about the triangle? Well, PQ, so the length of the vector PQ is half the length of the vector BC. Okay, well it tells me this. If you join up two midpoints of a triangle, then the line you draw has got to be parallel to the third side. Because we ended up with vectors that were basically equal but half the length, so they're going in the same direction. So I know they have to be equal. But the other thing we know, if we're joining a midpoint to a midpoint, then it's also going to be half the length of the third side. How about BR and RC? Let's put those in terms of A and C. Well, BR is a third of BC. Remember, they gave us that information. And we said BC was C minus A, so it's a third C minus A. What about RC? Well, RC was 2/3 of BC. So that'll be 2/3 C minus A. But this being able to write all the different vectors in terms of 1 or 2, this idea becomes real useful in proving different properties. Show that AR ends up being 1/3 2A plus C. How could I get AR? Well, AB plus BR, boom, I put them together, smashes out the B's, I've got AR, and I think we have expressions for AB and BR. Well, AB was A, and we worked out BR in the previous part, so add those together, and we get 1/3 2A plus C. A little introduction to vectors.